introduction, actual word. You can have an intro, you can have an outro. So, as is traditional, the last lecture is basically going to just be a recap of stuff, maybe a few gratuitous exam hints, maybe I'll show you some actual exam questions to prepare for. And then once I've done that, Steffi will do the same for her bit, or something for her bit. I don't know, we haven't really spoken about it at length, so it'll be fine. So, as you will no doubt be aware, there's exams coming up, so most of you will have 2, some of you 3 of those. The 450 exam I think is quite late. It's towards the end of the second week, so it might not be your immediate focus. I don't know where the other exams are. It's a fairly typical exam in that it's 3 hours long and you're not allowed anything except you, your awesome intellect, and some pens. You shouldn't need anything other than you, your awesome intellect, and some pens. If there are calculations involved, they will be simple, but certainly at this level we're not too worried about whether or not you can multiply 6 and 7 and get whatever 6 times 7 is. We're worried about the ideas and principles and things. There'll be 3 questions, 60 marks in total, 20 marks on each, plus 20 marks for each of the assignments, which you will get back very soon now. I was sick and then away last week, so I just have to send the emails and make sure I send the right email to the right person. So I need some quiet time to make sure I get that right, but that should be this afternoon. So the questions will be on the 3 main parts we covered: camera calibration and tracking, graphics and rendering for AR, and gesture detection and recognition. That's more or less what we said at the start of the course, so hopefully no surprises there. Past papers are a good guide for style, but we've changed a reasonable amount of the content, and that happens with this. For some of the newer stuff, I'll try and put together a sample exam paper with different questions, the ones I'm actually going to ask you, so that you can get some idea of that. But we have done in the past things like motion tracking, SLAM, augmented reality, neural networks for object recognition rather than gesture recognition. So there will be some material on past papers. But if you're looking at past papers and thinking, epipole geometry, we didn't really do that, that's because we didn't really do that, so it's probably fine. So there's a bunch of new stuff there. Usual sort of exam advice. I try not to write exams, or we try not to write exams where time pressure is the thing. I have sat exams where the question was essentially, how much calculus can Steve do in 3 hours? And no one was expected to finish that exam, and you were just supposed to go frantically for 3 hours. I didn't really enjoy that experience, so I don't feel the need to inflict it on other people. So read the questions carefully, because quite often we're asking something quite specific, and if you tell us stuff about the general topic but not the specific thing we're asking for, that limits our ability to give you marks. And when writing marks, when marking exams, I'm aware that under exam circumstances, various weird things can happen in your head. I know they happen in my head, even when I'm not in an exam. So, we're trying to give you marks, basically. So do what you can to help us. We'll give you some marks. You'll get some marks. Everyone will be happy. We'll move on with our lives. So write the key points clearly. It's okay to use bullet points. Pictures are often useful. Show your working and reasoning, so that even if you reach wrong conclusions, if you reach them by a good method, then that's all good. And number your answers so that we don't have to guess which bit you're answering. I expect you've all done enough exams that that's all fairly well understood. Given that you've made it through to 4th year, you've answered and done enough exams and done well enough in them that you've probably got this stuff sorted, but it's worth going over again briefly. Is there any questions about the structure of the exam or If you look at past papers, you'll see what the exams look like. There's usually a page or two of questions on each of the three parts, so you end up with sort of a 6-page exam. It might be a 6-page exam this year. So, going through my stuff, one of the first things we looked at was homographies and calibration. So homography estimation is this process of going from mapping essentially one plane onto another. And we can view camera calibration from a target like a checkerboard as finding a homography where one of the planes is the plane of the target and the other plane is the image plane of the camera. Yep. And so what we want to do is to find the relationship between points on the target and points in the camera using some sort of mathematical model. So that idea of homographies being this map between two planes and what the two planes are in the calibration case is really the motivation for this, so it's quite important. That led to this big pile of maths, which I'm sure you all remember very fondly. Should you need any of this, I will write it in the exam paper. So if you need this equation, I'll write it down in some form. So lots of symbols, but it's just matrices and vectors, so the maths itself isn't that complicated. We're not talking elliptic curves or quantum theory or wave equations, so it could be worse. And the important thing about this is that it has this geometric meaning associated with it. So if you look at past papers, there's quite often things where I'll throw an equation at people and say, what does that mean? So what's K? And there I'm looking for K's, the camera calibration matrix that tells you about the internal properties of the camera, like its focal length. I'm not that interested in you being able to write out that form of K, but if you can do that and you can say F is the focal length and C is the centre and S is the skew, then that's one way to answer the question, but you can just do it by talking in general terms. You know, an R, here are rotations, T's are translations. So the basic model we had there is that we've got these 3D points, get a stick. 3D points in the world get projected into 2D points in the camera. K, as I said, is the camera calibration matrix and does all that stuff. R is a rotation, T is the translation of the camera. So that moves the camera from the origin to be at some other place looking in some other direction. And the equivalence here is because this is a homogeneous equation with the vectors with the ones at the end, which means that everything's only defined up to a scale. And that, as we saw, makes a lot of the solutions quite convenient, but means that we have to deal with the scale, unknown scale all the time. And in the case of the camera calibration, all of our 3D points lie on the plane z equals 0, which basically removes this column from the matrix and gives us a 3x3 matrix, which is a homography. And that's why homographies are useful for camera calibration. That led to this big bunch of equations here, which you don't need to remember this bunch of equations. Just look it up, that's what I do. Usually in my notes, because that's where I wrote it down. But basically there's a big matrix, which is to do with the matching points between the two planes, your unknown homography entries, and it all equals 0. We get 2 equations per point, so we need 4 points, even though we've got 9 things, so why we only need 8 equations for 9 unknowns is important. The fact that you get the trivial solution of your homography is 0 might be important. The fact that you need a normalizing transform. And again, the reason for that is some of our measurements are really big, like pixels in an image, so they would be, 1,000. Some of our measurements are really small, like 1. And so you get an imbalance in the numeric solution there. Mathematically, totally not a problem. computationally makes your answers go horribly wrong. And we kind of solve this equation using singular value decomposition. Again, I'm not going to ask you to do singular value decomposition in the exam. If I did ask you how do you compute the singular value decomposition, use a matrix library as a perfectly acceptable answer, because that's how you compute the singular value decomposition. But this term that we're minimizing here isn't that meaningful, and so we have this concept of reprojection error, which is more meaningful. And again, reprojection error is if we end up with this model where we've got 3D points in an image, if we project our model 3D points back into our model camera, they should lie near the image points. We want to minimize the sum of those square differences. So that's a fairly high level view of the homography stuff. And we went through everything in a lot more detail for 2 reasons. Firstly, to explain why it all works rather than it just being magic. And secondly, because a lot of the issues that come up here, like having an equivalence rather than an equality, or having the zero solution, or needing to minimize some more meaningful term afterwards, come up a lot in different contexts, both in computer vision and in numeric computation generally. So it's kind of your spinach time, I guess, for that. So that's that stuff. Is there any questions about that? And kind of the level that I'm describing things in there is sort of the level of understanding that we require for the exam. So you might need to describe the normalizing transform, basically what it does, but you're not going to need to do the maths for it or anything, because why would you do that in an exam? It's not, no. So it's more important that we have that high level understanding. So to do this, we use the checkerboard because the corners are easy to find, but we'd like to do this in general with random scenes in the world. So we looked at features and pose estimation next. And we looked at 2 sorts of features. Corner features, which we used in KLT tracking, which is Kanade, Lucas, Tomasi, which doesn't matter really. As long as I know what you're talking about, you can call it what you like. And these blob features, which have got a size and orientation associated with them. Now, these corner features, when we're doing tracking, where we have one frame and then we have another frame immediately after it taken from almost the same position, we can get away essentially with just using little patches of the image as our descriptors to track around, because the appearance of things don't change too much from one frame of the video to the next, essentially. So the tracking case, we can use these simple detectors and descriptors. If we want to match images taken from very different viewpoints or at very different times, that starts to break down because the appearance of the features changes a lot. And so we looked at blob features, which are what these are, which have got a characteristic size and an orientation. And we looked at SIF descriptors a little bit, about how you can make descriptors that are robust to scale and orientation and lighting changes and so forth. And when we're matching, we search the whole image for matching sort of, we've got a feature in one image and we search all the features in the other image for a match, which becomes very expensive. So we looked briefly at KD trees and how they can speed things up. But the key thing here is that when we're matching rather than tracking, we get big changes between images. And so we need to use methods which are robust to that. So we can't just look near where we were last time. So we need to do this whole image search matching. And we need to have descriptors that are robust to changes in appearance, like illumination or rotation or whatever. And depending on what we're doing, we might have a tracking case or a matching case. So if you're doing SLAM, where you're driving a car along the camera, you might be able to get away with tracking, which simplifies your problem quite a lot. So once we've got those matches, we can do pose estimation, where we estimate the position and orientation of cameras and also the 3D structure of the scene. And this is building up towards SLAM, which is what you need if you want to do good augmented reality, where you actually have virtual objects and real objects being consistently portrayed. So what we get from two images is we get 2D to 2D matches, which might be through tracking or through matching, doesn't matter at this point. And if you know the camera pose, you can triangulate matching points basically by shooting rays out from the camera through the image points, and because they come from the same point in the world, they should intersect nearly, and where they come close is where the 3D point is. In past years, we've talked in a lot more detail about how that stereo stuff works, but that high level overview is really all we had time for this year, because we had other stuff to do. So looking at past papers, there'd be lots of questions about epipolar geometry and fundamental and essential matrices and things, which is all very interesting stuff, but not something we really focus on. If you've got a bunch of matches, you can also estimate the camera pose. So you can estimate both where the camera moved and the 3D structure, which means given two images, you can reconstruct some 3D information. So this kind of gets us started, but once we've got a 3D model of the world, this is a bit more expensive and error prone than we would like. And so we switch to perspective pose, or perspective 3-point pose, or perspective endpoint pose, where we've got 3D points matched to 2D points. And we saw that if we had 3 of those, that essentially constructs tetrahedron. So we've got 3 points in the world, make a triangle. Triangles are good because they're nice and rigid and they're guaranteed flat. And then we've got our camera center, and that gives us 3 more rays, and then you can do reasoning about the angles and edges and everything in order to figure out the pose of the camera given that 3D thing. Yeah. Again, the details of that maths aren't really that examinable. They might ask you about some equations, but it's the notion that you need 3 points. Why do you need 3 points? Well, each point gives you 2 constraints, because you get an x and y in the image, or u and v in the image. So you get 2 equations out of each point, and you've got 3 unknowns, which are the rotation and translation of the camera relative to the scene. And so those sorts of counting arguments, why do you need 4 points for homography? Why do you need 5 points for this one? Why do you need 3 points for this one? Come up quite a bit. And usually that's just a counting argument about each point gives me 1 or 2 constraints. I've got this many unknowns, divide constraints by unknowns, or unknowns by constraints, and get your answer. So there's all that sort of stuff. Any questions about that? So then we got on to SLAM. So this is LSD SLAM, because they've got the best video. Good reason to image shot. So the idea with SLAM is that you run around with a camera, or cameras and other sensors. So in computer vision, we like to do it hardcore and just use a single camera. If you're actually doing driverless cars, what you do is you put about 50 cameras on the car and a LiDAR scanner and some inertials and a GPS unit, and you fill the trunk with compute power, and then you beam it all back to base and do all that. But with a single camera going around, so this is 2 cameras for this one, you can compute the shape of it. And we've got 2 problems we're trying to do here, which are figure out where the camera or the vehicle is moving, and to recover a 3D model of the scene around us at the same time, which is the simultaneous localization mapping. There's a bunch of ways to do this. One of the simplest ways that we looked at was the expectation maximization approach. So you end up with this kind of chicken and egg problem where if you know the 3D scene, it's easier to figure out your localization. If you know your localization, it's easier to figure out your 3D scene. And so when you have a chicken and egg problem, you either have to build a chicken or lay an egg without a chicken. So you basically assume that you've got a solution to part of this to start with, and then you assume that's correct, solve the other one, assume that's correct, solve the other one, and you iterate backwards and forwards to refine it. And so you can start off with a dinosaur, and several million years later you end up with a chicken. To stretch that analogy well past its breaking point. So basically you start with, say, a stereo pair, you recover a bit of the scene, and then you do pose estimation to figure out a bit of localization, and then you reconstruct some more of the scene using multi-view stereo, and then you do pose estimation of multi-view stereo, pose estimation multi-view stereo. So you have an expectation of what your motion is, of your scene, and that allows you to maximize your certainty in your location, which allows you to improve your estimate of the scene, which allows you to get a better estimate of your location, and so forth. And that general division of the problem into those two parts and the way they play together is what's important there. We looked at FastSlam in a bit of detail, which uses Kalman filters and particle filters and whatnot. I'm not going to ask you about Kalman filters and stuff in the exam because you did that in the assignment, so I'm sure you don't want to hear about it again, so we won't talk about it anymore. The other thing with SLAM is loop closure, which is when you go around in a circle and you end up back where you came. I don't know if this is about to do a loop closure or not. And you find that things don't quite line up, so then they can be joined together and that loop gets corrected and closed, and you can then correct your map. So it's going around and it's come back round on the loop, and then you can see there was that kind of shift in the model where it realised it done a full loop and then it kind of corrected the whole thing to make it all consistent. Yeah. So that was SLAM, expectation maximization approaches, loop closure is a problem, things like that. And apart from the Kalman filter, particle filter stuff, which was really the assignment, that's pretty much what I remember doing in the first bit. So are there any questions about that bit, or anything you remember doing that you think I've missed out and therefore probably isn't in the exam? So then Steffi did some stuff, which she'll talk about in a little bit. But we talked about gesture recognition, and we talked about a couple of things. The first one being these point distribution models. And this is where you model your object as a bunch of points. So we looked at leap hand tracking because I couldn't find the data set I was looking for. But the other way to do it is that you've got your hands, which are beautifully drawn as always, and you have a bunch of locations around them which become your points. How do you find them? Yeah. So to make a point distribution model, you need to align all of your data. So you might have a whole lot of different hands at different locations. But we assume that they're all roughly the same shape, so we don't do Simpson's hands with only 3 fingers or anything like that. Though you can make models that allow for missing fingers or whatever. So we need to align them, and Procruste's analysis is the way to do that. So what we get, so these are a bunch of the link tracked hands, and you can see they're all over the place, all different angles and things. And so Procruste's analysis estimates a rigid transform which takes these hands and lines them up. So again, what I did for the link tracked hands is I only used the points that were on the palm of the hand because the fingers were whipping around quite a lot. And you first translate them all so that on average they're at the origin, so that they're all in basically the same place, and the origin's a convenient place because it means you can rotate around that point easily, and 0 is one of the nicest numbers to work with as long as you're not dividing, because adding it is easy and multiplying by it is easy, but sometimes a bit dangerous. So you translate them, then you scale them so they're all roughly the same size. Not so much of an issue here because they're all my hand, but if you had a data set from lots of people, you need to do that. And then you figure out the rotation between them in order to line them up. And the rotation is tricky. As usual, we use the SVD because it answers all of our questions. And then you end up with all the hands aligned here and only the fingers wiggling around as the difference. So this first step isn't really making a point distribution model, but it's really important to get all the data into a kind of uniform representation so that you can look at the variations you're interested in, which are in this case, the change in the finger positions, and not the variations you're not interested in, like where is the hand or what orientation is it at. Once you've done that, you make a active shape model, point distribution model, it's too many models, which consists of a mean hand, which is the average hand, not a cruel hand. So this is the average over all your training data. So the training data, in my case, had grasping, pointing, and gripping. And so the average is kind of half open and headed towards a pointing gesture a little bit. So this is kind of close to both gripping and open and pointing, so that's not an unreasonable average. And we estimated these characteristic modes of variation, which have a bunch of nice statistical properties. Firstly, they're all linear. You just add them onto the average to get other hands. They're all independent of each other. They're all orthogonal or at right angles in whatever high dimensional space you're working in. And the really nice thing is that they have a weight associated with them, and what you typically see is that the first few weights contain most of the variation you're interested in, so they allow you to give a very compact representation of the model. So in this case, 90% of the variation was in the first two components, which isn't that surprising because there's only 3 gestures, and if you've got 1 gesture, you've got no variation. 2 gestures, you basically got variation from one to the next, and 3 gestures adds a second mode of variation. So the first one more or less goes from a closed hand to an open hand, and the second one goes from a closed hand to a point. So you can see that the different clusters that we had in the data set turn up fairly directly in these modes of variation in this case, because it's a simple case. If you've got more modes of variation, they kind of get entangled. But we can use the weights which are used to create particular instances as our model. So rather than saying, I'm going to model the hand with 28 3D points, or however many there are on the model, which is a 70 whatever dimensional data set, and I can't think about 78 dimensional space. It makes my head hurt to think about 3D space, so I'm not going to 78D. We can think about it essentially as a 2D space of this variation, and 2D I can think about. And it means we just represent a hand as basically a couple of numbers in this case, which is how far along this axis are we, how far along that axis are we. So this is a point distribution model because it models the distribution of the points. So, and we saw that I could wave my hand over the leap and have it change colour when I did different gestures. To use that for classification, we first looked at nearest neighbour classification. So you take the average set of weights, so in this case it might just be a couple of numbers for each class, and so we get a bunch of weights. So if we just plotted two weights there, we would see, hopefully, that all of our open hand gestures were very big on the first weight, because they'll be down this end, and they're probably in about the middle on the other weight. So, very big on the first weight, about the middle on the other, so you get a whole lot of open hands there. Our pointing gesture would be very low on the second weight and probably about the middle on the first weight. So we'd have a whole lot of pointing. And our closed hand would be low on the first weight and big on the second weight. Probably a bit more spread out than that, but anyway. Actually, I'll spread some of this out. Spread out. So if I've got a new hand somewhere, I can just basically say that open hands are basically about here. Pointing hands are basically about here, and closed hands are basically about here, which is just the average of all the instances. So I've got a new instance here. It's nearest to open, so I just call that open. And that's the nearest neighbour classifier. So we compute all these means, and we find the arg, I should have corrected that because I got it wrong last time, argument rather than argmax. Anyway, the nearest one. Okay. This has a couple of problems. Firstly, no matter where you put this point, it will give you a classification. So if you put it here-ish, which is roughly the same distance from all of them, it will just give you the nearest one, whichever it might be, whereas it's probably not any of them. The other thing is that these are more spread out than those. So if you want to know what this is and you have to make a decision, it's actually more likely one of these because there's more variety there. You know, you can get quite closer to there than there. So the Mahalanobis distance, which I always try and say very quickly, does this for us, and it includes the covariance in this computation. And the inverse covariance, in fact. So basically, the bigger the spread, the smaller this distance is going to be for a given point. So if your data's all spread out, you can be further away from the average and still be considered part of that set. If your data is very tightly clustered, even a small deviation will exclude you from it. If you take that out and just put it in the identity matrix, you get the square distance, normal square distance, so it defaults back to nearest neighbour if your covariances are all 1. And what that does is two things for us. Firstly, it allows us to model the fact that these are more spread out than these other ones. But also lets us set a threshold where we say, beyond this point, you're just not considered a closed gesture. Because if you've got your covariances right, this distance comes out essentially in squared standard deviations. And if you remember bell curves, which we use a lot as an approximation, there's a 95% chance that you're going to be within 2 standard deviations of the mean on a bell curve, and a 99-point-something% chance you'll be within 3 standard deviations. So if this distance is bigger than 3, you're probably not this. And if you're probably not everything, then you're probably not any of them. And so you can say this is an unclassified gesture, which a nearest neighbour classifier can't do, because it's always going to give you an answer. And if you've got 2 overlapping distributions, this will tell you which one is most probable given the statistics that you've observed. So if you've got a very spread out set and a very tight set inside it, if your sample is in here, you would get associated with the spread out set because you're only maybe 1 standard deviation away from its average. Even though you're closer to the red set, you're more standard deviations away because it's tightly clustered. So it gives us a much better thing. So the matter on this distance comes up a lot nice as well. The other thing we looked at for that was active shape models. So the point distribution models assume that you just get these points magically. And if I've got a video of my hand waving around and I'm trying to find feature points around the outside, that's not true. It's quite hard to do that. What an active shape model does is it takes the frame of the video and it assumes you've got an initial guess of where the object is. So the first one needs to be initialized somehow, possibly manually. But after that, you just use the previous guess as where you were, and then you update your shape model in order to track it. So you're basically trying to wiggle your shape around so that it lines up. And you can do that by changing the overall transform or the shape parameters within the bounds of probability. And we need to see how well our model lines up with the image. And often that is that we want these points to be on edges in the image, so areas of high intensity, because the boundary of the object you're tracking is often what you're tracking, and you can see that change in appearance. So these active shape models are often used for things like face expression tracking, and there's more advanced versions that we looked at, things like active appearance models, which add in the colour or intensity of the image, as well as just the control points. And so that can model things like when you smile, you get these folds, which are then darker than they were when you're not smiling. And things like that, which are commonly used there. But the basic idea of the active shape model, I think, is the key one there. Okay. So this is kind of the traditional approach to computer vision. We build statistical models, and then we say how likely is that to happen. Are there any questions about that much? You've done an excellent job teaching me through this semester. Or something. So the last thing we looked at was neural networks. And I know there's a lot of crossover between the neural networks paper and this paper. But for gesture recognition, the networks that we looked at were 3D convolutional neural networks. And that's really where it's at for video analysis in computer vision. So again, these convolutional neural networks do 2 things. They have convolution, which you can think of as like filters in Photoshop, and then they have pooling, which downsamples images. In a 3D convolutional network, you get these, rather than 2D image, you get a 3D volume of video, if you like. So if you imagine all the frames of a video stacked up into a cube. And that works exactly the same way, except that rather than being square filters of numbers, your convolutions become little cubes of numbers. You apply them in exactly the same way, and you get cubes of numbers out at the other end. So essentially that means one more for loop in your nested for loops when you do your filter, because it's one more term in your sum. So rather than summing over x and y, you sum over x, y, and z, or x, y, and t for time in this case. So that doesn't make things conceptually more difficult, but it does mean you need a lot more memory, a lot more processing power, but fortunately NVIDIA keeps on making scarier and scarier graphics cards, so that's not a problem. You just say, I'll get myself a Quadro with 24 gigs of graphics RAM and hope that it works. And it does. So what you have as your input is a little sequence of video of a hand doing a gesture. You do a whole lot of these convolutions, which through training learn various features of that which are characteristic of specific gestures. And then you put it through some sort of classifier at the end, which is almost always a fully connected neural network, which is a fairly traditional, as in since the 80s, neural network classifier. And out at the end you get a bunch of classes, and we saw these classifying 19 or 20 odd classes, things like 2 fingers left or right, or up or down, well, left or right, or the OK gesture and the thumbs up gesture and lifting and pushing and all sorts of things. So the details of how you use back propagation to train these things is largely sort of 420 stuff. The application of them to gesture recognition, the 3D convolutional stuff is really more 450 stuff. So you need sort of a higher level there than you might in other papers. We also looked a bit at the problems you have with deep networks. So there's these adversarial networks where, this is a bus, this is a bus, that's not a bus, that's a bus, that's a penguin, that's a peacock. Obvious, really. So we have these problems of the networks being kind of inscrutable. It's hard to tell exactly what they're doing. You can trick them into giving foolish results. And also problems with training data. So in order to train these things, you tend to need a lot of training data, which is labeled, and that can be expensive to get. And you have issues with your training data and how representative it is, which enables me to give you actual exam questions that I have written in the exam. Steffi can back me up on this because she's also seen the exam. So as well as the general issues of neural networks, there's these issues around training data bias. So I'd like you to talk a little bit about that using face recognition as an example in machine learning systems, and how much you think that is an issue for gesture recognition, sort of hand gesture recognition. You might think it is or it isn't. That's fine. I can see ways you could argue either way, and I'm interested in how you argue that. And to start you along that, there's a TED talk. So this is Joy Buolamwini, and she's a researcher at MIT, or was when she did this. And I'll see if that video will play with sound and everything.
Hello, I'm Joy, a poet of code on a mission to stop an unseen force that's rising, a force that I call the coded gaze, my term for algorithmic bias. Algorithmic bias, like human bias, results in unfairness. However, algorithms like viruses can spread bias on a massive scale at a rapid pace. Algorithmic bias can also